I'd like to welcome you to a very special colloquium given by our colleague Jack Milnor. Most of you are probably very familiar with Jack's very influential work. If you're not, he's received too many prizes to mention here, but they include the Fields Medal and the Alpha Prize. Jack is not only famous for his very profound contributions to topology and other dynamics and other areas of mathematics, but also for his incredible skill as an expositor. I think that mathematicians of my generation all feel like we learned mathematics by reading Jack's books. And I'm sure that we'll see another example of his wonderful expository skills today. So I'd like to now introduce his colloquium entitled Points on the Circle from Pappus to Thurston.
Thank you. Can everyone hear me? Yes. Okay. Well, the object of this talk will be to start with some very simple-minded ideas and show that it leads quickly to quite interesting mathematics. I'm talking about an area that's been worked over by many people over the years, so it's hard to give exact credit for who first did what. But in any case, let me proceed. So the circle I want to talk about is the real projective line. So we can think of this as a round circle, or I don't trust these newfangled pointers, so I brought my own. So we can think of the round circle, or we can think of it as the real line, but together with a point at infinity. And you identify these by the classical stereographic projection method from the North Pole. You draw a line from the North Pole through a point on the red circle and follow it till it hits the blue line. And as the point moves up towards the North Pole, this point will move out to the point at infinity. Now, projective transformations were defined classically by direct geometric construction. You take two lines in the plane and a point off the lines, and you project from the point P, then the point Q on the blue line corresponds to a point R on the red line, and this gives a one-to-one correspondence, providing you count points at infinity along the lines. For example, suppose that Q moves out until the line from P to Q is parallel to the red line, then the corresponding red point will be the point at infinity. So that's the geometric description. A much more convenient way of dealing with it is algebraically by defining a map from R together with the point at infinity to itself to be, well, we can call it projective or fractional linear if it has this special form. And these two definitions are more or less equivalent in some sense, but this is much more convenient because we can compose these things directly to form a group, whereas if we're working with lines, we'd have to consider many different lines, and it would be a more awkward construction. But if you just choose natural coordinates on Q and R, you'll find that it amounts to this kind of formula. So this is a three-dimensional group. Here we have four coefficients, but if we multiply all of them by a constant, then we get the same mapping. So it's a three-dimensional group. And the fundamental property is that the action is three-point simply transitive. So that means if we start with any 3 points on our hat, any three labeled points, then we can take any other triple of labeled points, there's a unique fractional linear transformation which takes the first points to the second points. If there are any of you that don't know this, It's a nice exercise. Okay, well, I want to start out, since I advertised I would talk about Pappus, who lived about 1700 years ago. He constructed an invariant associated with 4 points along a line. Just so you take the blue line, we have 4 points A, B, C, D. Given the distances from A to B, B to C, and C to D, he constructed a rational number as an invariant and proved that it's invariant under projective transformation. So even though the distances are quite different, the proportions between distances are quite different, he proved that this invariant is the same for the blue points and the red points. Actually, not much is known about Pappus. The only way we know more or less when he lived is because he reported seeing an eclipse during his lifetime. Eclipses, of course, are easy to date, so we know it was about 1700 years ago. Well, that was the geometric definition. Algebraically, it's much easier. Now, there are various different people use different versions of the cross ratio for different purposes. I'll give my favorite one, which is to think of the numbers A, B, C, D as being the A and B as being the top two elements of the matrix, and C and D as being the bottom two elements, and then forming the product of the differences between row elements and divide by the product of the differences between column elements. So the reason I like this is it makes it very easy to see that there are certain invariance properties. For example, if we interchange the two rows, nothing changes. If we interchange the two columns, nothing changes. So these are two elements of order 2 generating a group of order 4 of elements which don't change the cross ratio. Now, there's one restriction here. Usually you want to assume that the 4 variables are distinct, but it still makes sense if only 3 of them are distinct. The only difference is that we have to, since the denominator may be 0, we get not a real number, but a number in our hat. In fact, you can easily see that, well, first of all, there's a unique continuous extension to the case where A, B, and C, and D are in our hat. For example, suppose A tends to infinity. Then the first factor in this first two factors, A minus B over A minus C tends to 1, so we're just left with a simple rational function of B, C, and D. Well, the reason I like this formula is because it makes it perfectly obvious that the cross ratio is 0 if and only if either A equals B or C equals D. And notice I can't have both, because if A equals B and C equals D, then we wouldn't have 3 distinct points. If they're not 3 distinct points, you'll quickly get into trouble getting answers like 0 over 0. And similarly, the cross ratio is infinity if and only if either A equals C or B equals D. And the third is not quite as obvious, but it's easy to check. The cross ratio is equal to 1 if and only if 2 diagonal elements are equal to each other. So I've listed all of the ways that 2 elements can be equal, and since these are all if and only if, we conclude that the 3 points are different if and only if the cross ratio is not 0, 1, or infinity. And it's easy to check that all possible values occur. For example, this is well, with this choice of cross ratio, it's a rather hard formula to remember, but it's not hard to check. Okay, now the points, the subject of the talk will be many points on the circle. So first of all, suppose we start with, well, in this case, what is it? 7 distinct points on the circle. Then, definition, the moduli space, M0, 7 of R, or I'll write just briefly MR, M7, is the space of equivalence classes of n tuples of distinct points on R hat modulo the action of the group of rational linear transformations. In other words, this list of labeled points and this list of numbered points represent the same point if and only if there's a fractional linear transformation which takes each pj to the corresponding qj.
Now the points are all distinct, right?
So far, they're all distinct. Well, this is a sort of a definition which looks simple-minded, but it's a little hard to get a grasp of what it means, because projective transformations aren't just rotations, they're much more general. So for example, we can choose a projective transformations which takes these 3 points, 5, 3, and 7, closer and closer together. So but the element of moduli space won't change. On the other hand, since the group is 3 point simply transitive, we could spread 3, 5, and 7 out, and then all of the other points would have to cluster close together. And the definition can't tell the difference. That's the whole point of why this is an interesting object, actually. Well, first of all, a simple transformation. It's an easy lemma that these two n tuples represent the same point of moduli space if and only if all of these cross ratios are equal. Well, we could say all corresponding cross ratios are equal, but it's enough to consider ones where the hi, j, k are in increasing order. The corresponding statement for the others would then follow very easily. So this means we can embed Mn into the n-choose fourfold product of circles. We just, corresponding to each point in moduli space, we take this n-choose 4 tuple of real numbers, the cross ratios. And it's easy to check that this is an embedding. So we have the moduli space, whatever it is, can be embedded in a product of a large number of circles. And now the definition I'll use is very simple-minded. We just take the closure. So we look at all points of this big torus, this big product of circles, which can be approximated arbitrarily closely by points from this subset, the image of Mn. And their theorem is that this is this is a smooth, compact, real algebraic manifold of dimension n-3. Now, let's see, there are various parts to this statement. The statement that it's compact is obvious. The closure of any set in a compact space is compact. Dimension n-3, it's fairly easy to count that there are n-3 independent variables. Here's a intuitive proof, at least an intuitive proof that M is a real algebraic set. If the pj are all distinct, so I'm first of all looking at Mn. So if the pj are all distinct, then we can put the first 3 at 1, infinity, and 0. And then we'll have this cross ratio is equal to pk for all k. Well, here the P4 up to Pn can be chosen more or less freely as long as we avoid collisions. So we certainly have an n-3 independent variables. And so if we know what all of these numbers are, then we can compute all of the cross ratios. So that means that all of these n choose 4 cross ratios can be computed just in terms of these, or as functions of the pk. So expressing each of these as a function of the pk, we get a set of n minus 3 rational equations. And clearing denominators, we get a set of polynomial equations. And these polynomial equations must be satisfied for every element of Mn, and hence their set must be satisfied for every element of Mn closure. So one has to get a proof, one has to work a little harder than that, but that's the basic idea. But there's one other point to the statement which is much harder to prove, the proof that it's a smooth manifold. And this is worked out in complete detail in their book. It's an elementary argument, but I won't try to it's rather complicated, and I certainly won't try to prove it. But it is a basic fact that this is a smooth submanifold of a large torus. Well, the simplest case, n equals 3, well, there are no cross ratios at all, just we define M3 to be a single point. For n equals 4, there's just one cross ratio. So Mn is a subset of R, consists of just R hat with the 0, 1, and infinity removed, or if you like, it's R with 0 and 1 removed. And the closure is obviously the entire circle. We should think of this as a cell complex with 3 vertices and 3 edges. There are 3 exceptional points, 0, 1, and infinity, which correspond to elements of moduli space represented by only 3 points, where one of them is doubled, and the remaining points, which are represented by 4 distinct points. Well, the next case, M5, gets much more interesting. It's what I call a hyperbolic dodecahedron. So it's hyperbolic because it's a closed surface of negative curvature. It's a dodecahedron because it's tiled by 5 right-angled hyperbolic pentagons. Here's some attempt. It's very hard to describe. This is an attempt. These are pictures in the universal covering space represented as the unit disk with its standard hyperbolic structure. One is centered at a pentagon I called A, and the other is centered at the opposite pentagon, which I called B. And there are 12 pentagons labeled A, B, and 0 through 9. And any 2 pentagons with the same number are to be identified with each other. And you can tell what vertices are to be identified just by checking what 4 pentagons they're adjacent to. So, for example, 3, 4, 5A here will be identified with 3, 4, 5A here, and so on.
0 through 9 plus A and B?
Yeah. That was just sort of an arbitrary choice. Well, as I said, it's very hard. This thing is a very tightly bound together, and it's hard to visualize it. This is a model which Myra knitted, but it... crocheted, excuse me. But it doesn't quite succeed in showing the complexity because it has one boundary curve and one boundary figure 8, and they have to be pasted together in a complicated way. It's a very hard object to grasp. Well, the interiors of the pentagon are the elements of M5, of course, and all the brown lines are the things which are added to form the closure, the completion, or compactification, whatever you want to call it. Well, it's interesting to compare this with the Euclidean dodecahedron. So they both have 12 pentagons. They both have an isometry group of order 120, but they're different groups. In this case, for the dodecahedron, there's the antipodal map, which takes each point to its opposite point and each face to its opposite face. And that generates a central subgroup of order 2. The whole thing is just the direct product of the cyclic group generated by the antipodal map and the rotation group, which is the alternating group on 5 elements. The symmetry group is a symmetric group on 5 elements. So given any change of labels, any permutation of the labels, you get an automorphism of the space. Well, in either case, you can describe the automorphism group the same way. You can take any 2 pentagons here and choose any isometry from one to the other, and it extends uniquely. And the same is true over here. So there are 12 pentagons. Each pentagon has 10 isometries, 5 orientation preserving and 5 orientation reversing onto another. So they're altogether 120 isometries in both cases. In both cases, each face has an opposite face. I've tried to indicate this over here by labeling opposite faces with the same color, but I know that's rather hard to see. But A and B are opposites, and each integer j is opposite to j plus 5. So for example, you see up there that 7 and 2 are both colored red. 9 and 4 are both colored sort of violet, and so on. And A and B, of course, are both colored black. Well, we can compare Euler characteristics. They both have 12 faces. And in each case, each face is close to is adjacent to 5 edges, and each edge is adjacent to 2 faces. So the number of edges is 5 halves of 12, which is 30. But they differ in the number of vertices. Here there are 20, here there are only 15. And that means that the Euler characteristic is +2, and here it's -3, which is very different. So what can we conclude from this? Well, what can we conclude from this -3 in particular? Well, first place, it's a non-orientable manifold because any orientable surface has an even Euler characteristic. And second, it can't have any fixed point free involution because a surface with a fixed point free involution is just a twofold covering space of some other surface, and since it must have an even Euler characteristic. So this is rather weird. Each face has an opposite face. So they say the center points of the faces, each one has an opposite point. But this doesn't extend to any one-to-one map from the surface to itself.
Can you repeat that last sentence?
Okay. Every face has a unique opposite face. If you like, in both cases, every face has 5 immediate neighbors that you can get to by crossing one edge. It has 5 next to adjacent neighbors, which you can get to by crossing 2 edges. And it has one opposite face, which you have to cross 3 edges to get to. So it sounds the same, but in this case, this correspondence between faces extends to a correspondence between points, taking each point to its antipodal point. But there is no such correspondence in this case. There is no fixed point free involution. Well, let me just go through how you can understand some of this. Why are there 12 pentagons, first of all? Well, each top dimensional cell in Mn corresponds to one of the n factorial minus 1 over 2 different ways of arranging the labels around the circle. up to cyclic permutation and up to reversal of orientation, because our fractional linear group is allowed to reverse orientation. Well, you just start with any one of them and arrange the others in any way you like to the right. There are n-1 factorial ways of arranging the others after the first one. And then if we flip orientation, we have to divide by 2. So that's where this formula comes from. And for n equals 5, this means there are 12 two-cells. Now, so remember that the any top dimensional cell is described by an cyclic order of points around the circle. So here I've taken 5 points arranged in cyclic order around the circle, and how can we see what the edges will be from this? Well, the only way we can cross from one cell to another is if one of the points crosses over another. So if, say, C crosses over D, we'll switch to a different cyclic ordering in a different face, and the crossing point will represent an edge, or be a point of an edge. Well, there are 5 different ways, 5 different pairs of adjacent points. It's just convenient to represent this by drawing a straight line across here, separating these points from the rest. And furthermore, it's convenient to describe what happens by shrinking this point to a straight line to a point. So we get a diagram like this, where now we have 2 circles with B and C on one and A, E, and D on the other. And this is to be a case in which well, I was going to say the cross ratios are preserved, but there are only 3 points, so there is no cross ratio. But here, this point, this, and this are to have a well-defined cross ratio. And that cross ratio is a parameter along the edge, corresponding edge. Now, why do we want these to look transverse? Well, if you think of a transverse intersection, say, between 2 lines in the plane, xy equals 0, then you can split it up in 2 different ways. You can take xy to be plus epsilon, in which you join the 2 edges like that, or take it to be minus epsilon, you can join them like that. So you think of this as a kind of a swivel joint, where this curve can either go to here or to here. That will correspond to moving to one or the other of the 2 faces.
Two circles correspond to where the 2 points cross. I don't understand the 2 circles.
Okay. Well, I'm representing the possibility that B and C cross by drawing a line separating B and C from the rest and shrinking that line to a point.
Oh, okay.
Well, we can represent this much more formally. There's a formal embedding of MR plus 1 cross MN plus S plus 1 into MN associated with any partition of the integers between 1 and n into 2 subsets I and j. The only condition is the set I must have at least 2 elements, and the set j must have at least 2 elements. So whenever you have such a partition, there's a well-defined embedding of a product of 2 of these manifolds into the third. And we can represent it by this kind of a diagram where we have 2 circles intersecting at a red point. And here, on this point, we have the points of I in the order in which they occur. And here we have the points of j in the order in which they occur. And this circle represents a circle which we've collapsed to a point. I'm sorry, a straight line which joining the two, which separates one set from the other, and which we've collapsed to a point. And the assertion is that given any diagram like this, we have a corresponding element of the compactification Mn. In particular, the image of this is a union of codimension 1 faces of Mn, and every codimension 1 face occurs in this way. So I have to explain exactly how this works and what it means. But let me just say that we can iterate the construction here. Remember, we shrunk a line to a point and split one circle into two. We can do the same again, draw a line across here. And so now we have 3 circles. This one corresponds to the left. This one corresponds to this region. So now we have 2 red points corresponding to that and that. And the third one corresponds to the point of the right. So we still have all of the labeled points, and we also have 2 additional red points. And you can keep going. So the only condition is that you can iterate this as often as you like, as long as you have the condition that every circle has at least 3 distinguished points, whereby a distinguished point, I mean either one of the red intersection points or one of the labeled points. So here we still have a long ways to go, because all of these have more than 3 points. But each time you do this, you're decreasing the dimension of a corresponding cell. And when you can't go any further, you're down to a vertex, where then all of the circles have exactly 3 distinguished points. Well, how can we? So I've defined the closure in terms of embeddings into a torus defined by cross ratios. So I have to define what this construction is in terms of cross ratios. So in defining the Mn bar, I only considered 4 tuples in increasing order, which makes the definition easier, but is awkward when you actually want to do something with it, because you often want to permute the elements. So we just take 4 distinct points in any order. Then we can just take any sequence of points, Mn converging to a given point x, take the limit of cross ratios, and define this to be the limiting cross ratio. And in terms of this, and I can say that a point x belongs to the image of this map, if and only if every cross ratio in which the first 2 entries come from capital I and the second 2 entries come from capital J must be 0. Let's see, maybe I'll understand this better if I skip back back to this picture. So if we take any cross ratio where we take 2 points from here and 2 points from here, it must be 0. And that means if we take any, this is a limiting cross ratio now, but suppose that we approximate this by by definition, every element in M bar can be approximated by elements of Mn. And when we approximate, that means if we take 2 points over here and 2 points over here, the cross ratio must be very close to 0. And remember, cross ratio 0 means either that these 2 are equal or these 2 are equal. So cross ratio close to 0 means either these, well, cross ratio 0 means either that these 2 are equal or those 2 are equal. So what it means is we've sort of divided the world of this circle into 2 incompatible universes. In this from this universe, we can really spread these points out, but then any 2 elements over here will have cross ratio 0, meaning a point, if you're over here, all of these points look alike. They're all collapsed to this point, red point. Whereas if you're over here, all of these points look alike and they're all collapsed to the red point. And it follows easily that the limiting cross ratio can be defined completely just in terms of the cross ratios for this circle and the cross ratios for this circle, yielding the required embedding. Oh, okay, I've been through this. Okay, so for example, suppose we apply this to M5. So there are 10 partitions into subsets of order 2 and 3. That means we have 10 embeddings of M3 bar cross M4 bar into M5. But M3 is a point and M4 bar is a circle, so we have 10 circles in M5. These are just the 10 geodesics which we saw in the picture of M5. And each of these geodesics looks like M4, so it's a cell complex made up of 3 edges. So that means this is where we get the 30 edges in M5. We'd have 10 closed geodesics, each made up of 3 edges. Now, each of these geodesics also contains 3 vertices, but remember, each vertex is a place where 2 geodesics cross. So there are not 3 times 10, but only half that number of vertices, which is 15. So this is where we get the formula for the other characteristic. Now let's look at M6. Now there are 15 partitions into subsets of order 2 and 4. So that gives us embeddings of M3 cross M5, which is just M5 into M6. So M6 contains 15 copies of the hyperbolic dodecahedron. But also there are 10 partitions of M6 into 2 subsets of order 3. I'm sorry, I don't mean the, I'm sorry, this is, yeah, that's right. If we have 6 points, there are 10 ways of partitioning it into 2 subsets of order 3. So this gives 10 embeddings of M4 cross M4 into M6. But M4 is a circle, so this is a circle made up of 3 edges. So M4 cross M4 is a torus made up of 4 squares. And there are 10 different tori in M6, each one of them made up of 9 squares. So putting this all together, the 2 skeleton of M6 consists of 180 pentagons and 90 squares. These are very complicated objects. Remember also that this is a manifold which has the symmetric group of order, symmetric group on 6 elements is an automorphism group, so it has 720 automorphisms. Well, how can we understand what kind of object this is? There's a beautiful theory by Thurston describing all possible smooth closed 3 manifolds. And his conjecture was that every smooth closed 3 manifold can be cut up along either 2 spheres, tori, or Klein bottles into pieces, each of which has a locally homogeneous geometry. And he described 8 possible local homogeneous geometries. And he proved many cases of this, and it was finally proved in complete generality by Perelman. So it must apply to M6 bar. And how does it apply? Well, we already have 10 tori in M6, and they play a key role. So the theorem, if we cut M6 open along its 10 embedded tori, the remainder can be given the structure of a complete hyperbolic manifold of finite volume with 20 infinite cusps. This is a caricature of the beast. So there's a central hyperbolic manifold, which I won't give any details of, but it has 10 loops like this going out, where each loop has a cross-section, which is a torus. So there are the 10 red tori. And if we take a pair of scissors and chop off each of these red tori, then we have 20 things stretching out to infinity. So that's the 20 infinite cusps. You have to think of cutting this off and then thinking of it as made of taffy, just pulling it out to infinity to find a infinite thing which looks like a torus across a line, but where the size shrinks so that it has a finite volume. Well, one corollary from this, the fundamental group maps onto a free group on 10 generators, because you can just take a set of 10 loops, embed it, and this is a retract, and the fundamental group of the whole thing retracts onto this free group on 10 generators. So it has a lot of non-abelian structure.
Can I ask a dumb question? You've embedded this thing into a product of tori. Does Thurston decomposition have anything to do with the metric you get from the tori?
No, not at all.
Just, okay.
Yeah. No, because, for example, in the tori, these 10 tori are real tori. I mean, they have length and so on, and in the construction, we're shrinking them to points at infinity. It destroys the geometry completely. So it has lots of non-abelian geometry, non-abelian structure, but it also has lots of abelian structure, because each of these torus has a free abelian fundamental group Z2 plus Z2, and it follows from standard results that injects into the fundamental group of the whole thing. So it's a very complicated object. Well, here's an outline of the proof. So first of all, note that each 3-cell in M6 is bounded by 6 pentagons and 3 squares. We can see this as follows. We start by drawing a circle with 6 points around the boundary, and then each pentagon corresponds to a partition into 2 and 4. So the 6 edges of the red star, of the green star, correspond to the 6 ways correspond to the six pentagons. And similarly, we can divide it 3 and 3 by the 3 red diagonals. So we have 3 red squares, and when you figure out how all this works, we get an object which looks like this. Now, I find it very hard to draw this or explain it, but we can think of it as follows. Take two ordinary tetrahedra and put them face to face, so that one of them has a vertex at the top, one has a vertex at the bottom, and the 2 are joined in a triangle in the middle. And now take an axe and chop off the 3 middle corners, and we're left with the right object. That is, with a cell complex which has the right topology. Now, remember that it's easy to check anyway that there's 60 copies of this 3-cell which have to fit together to form a smooth manifold. Well, if we want to give some geometry to this manifold, we have to, first of all, it's easy to check that there are 3 faces which fit together around 4 faces which fit together around every edge. So the simplest way of getting things to match up around the edges is to have all dihedral angles equal to 90 degrees. But that's very far from true in this picture. In fact, you can't find any. It's impossible to find a Euclidean polyhedron which has this topology and has all dihedral angles equal to 90 degrees. In order to achieve it, we have to go into hyperbolic space. So let me take a picture, look at a picture in hyperbolic 3 space. So I start by taking a point A and 3 orthogonal lines of length L, and then taking the convex closure, which will be a hyperbolic tetrahedron. And by the construction, since these three lines from A are orthogonal to each other, the three dihedral angles along the edges from A will be 90 degrees. But what about the other edges? Now this is, remember, this is just one tetrahedron, and we have to paste two tetrahedra together to get our three cell. So take another copy of this and paste it together along the top face. Then if the dihedral angles are going to be, total dihedral angles are going to be 90 degrees, then we need dihedral angles along the edges, but along the three top edges to be 45 degrees. Well, it's not hard to check that this is impossible for a finite hyperbolic tetrahedron. To see that, suppose we take a vertex, say B, and take a little sphere around it. Then that sphere will intersect the tetrahedron in a spherical triangle. And since one of the dihedral angles is 90 degrees, one of the dihedral angles will be, well, this is a spherical triangle whose angles are just the three dihedral angles of these edges. One is 90 degrees, and since the sum of the others, since the sum of the angles of a spherical triangle is always greater than 180 degrees, that means that the sum, that we can't have 45 degrees. In fact, it's symmetric. It's an isosceles right triangle in the sphere, so the other angles must be strictly greater than 45 degrees. On the other hand, as L goes to infinity, these dihedral angles will tend to 45 degrees, because if we go farther and farther out, then the thing will get more and more pointed as we approach B, so the sphere will intersect the object in a smaller and smaller spherical triangle, which looks more and more like a Euclidean triangle. And the limit, as L goes to infinity, the dihedral angles will converge to 45 degrees. So we take the ideal tetrahedron constructed in this way, with edges going out to infinity, take two copies and paste them together, and we get a model 3 cell. But there's a cost, because we can only do this by collapsing the three squares to points and pushing them out to the sphere at infinity. But in this way, we see that M6, with the 10 tori or 90 squares removed, can be given the structure of a hyperbolic manifold tiled by 120 of these, that's 2 times 60 of these ideal tetrahedron. So that is the outline proof.
Is there something analogous to the dodecahedron?
Not that I know of.
This dimension?
I mean, there are, as I said, there are, 15 of the hyperbolic dodecahedra embedded in this, but it's a complicated object.
So when you look at the Jacob-Shalin decomposition, it just has hyperbolic pieces that are moved across tori, or?
Yes. Yeah, well, this is an example of what it is. It's a rather unusual example. Usually you expect the tori to separate, but here they don't separate. There's only one thing. Okay, to conclude, I want to change the subject, apparently change the subject completely, and talk about the associahedron. So about 55 years ago, Jim Stashev was studying associativity for spaces with a continuous product operation, and the analysis depended on a sequence of objects which we now call associahedra. So here, for example, is the A3, the associahedron for threefold products. If we have a non-associative product, then product ABC doesn't make any sense at all. But we can make sense of it by multiplying the first two and then multiplying by C, or by multiplying the second 2 and then multiplying by A. So there are just 2 ways of making a sense of a non-associative product of 3 elements. And if the product is homotopy associative, then we can get a homotopy from this to this. So this line you can think of as representing a homotopy from this, a possible homotopy from this product to this product. But if we take 5 elements, or 4 elements, then it gets more complicated. Now it turns out that there are 5 different ways of making sense of a 4-fold product. I mean, for example, we can first multiply B and C, then multiply by D, and then multiply it all by A, and so on. So we get, this object has the ABCD, the meaningless product, in its center. It has the meaningful products as its vertices, and the edges are cases where we've only put in 1 parenthesis, so it's not enough to define anything. But this BC is common to this and this, and this ABC is common to this and this, and so on. And this extends to higher dimensions. And now the amazing theorem is that each top-dimensional cell of M bar is isomorphic as a cell complex to AN-1. I'm not sure who first discovered this. It's been known for some time. Well, let me just try to outline a kind of proof. So this is the idea of a proof. Sorry? What?
When n equals 5, what does this give?
Well, it gives the top cell of M6, which you described, with 6 pentagons and 4 squares.
That's an associative.
Pardon? Yeah. So let me first of all describe what does the vertex of a top-dimensional cell of Mn look like? Well, the top-dimensional cell is represented by, in this case, for n equals 6, is represented by 6 points arranged in order around a circle. And now, if we pass to a face, we have to separate 2 of these or separate these into 2 sets. And doing this over and over, we get, doing this as often as we can, we get down to a vertex. In this case, we can do it 3 times since we're in a 3-cell, so we have to do it 3 times to get down to a vertex. Now, the usual procedure is to just shrink each of these lines to a point, and then we get a diagram of circles like this. Notice that this satisfies the Mumford criterion, that each circle has 3 distinguished points. So this is a standard description of a vertex of the M6. But we can do something quite different with this diagram. Suppose first of all, we have to remember that Mn corresponds to an n-1 associahedron, so we have to get rid of one of the vertices. Say we get rid of F, and put the other vertices in order around the circle, but just represent F by a long line. And now I claim that this will give us a prescription for making sense of a non-associative product. For example, we can take 2 along the bottom, B and C, and let this red edge represent BC. And now we take BC and D and let this red edge represent BC times D. And then this edge will represent A times BC times D. And finally, the top edge will represent that, which is one vertex of the associahedron. And you can do this for any vertex and get a similar diagram. And if you forget to put in some of the, if you don't have enough lines here, then some of these products will not be defined. You won't have enough parentheses put in to make sense. But in this way you get a one-to-one correspondence between the top cell of Mn and the n-1 associator. And that's the end. Now, these things have been studied by many people, so I certainly can't give a complete list of references, but here is some of the key papers. The most recent one I could find stuck on for good measure, and so you'll find many other references in these papers, and these slides are available on my webpage in case any of you are interested in following any of this up. So I'm open for questions now.
Is there anything systematic to be said about the topology of these spaces as n goes to infinity, or?
There is certainly a big literature. In particular, this paper gives a definition of the cohomology, a computation of the cohomology ring, and I think they're all non-orientable. I think there's also a set of generators and relations for the fundamental group, but I don't know how far that goes into understanding the fundamental group. But certainly there's an enormous amount of literature. Yeah.
So what would happen if I identified more of the red lines together? So, what if I had several circles intersecting at the same point? What would go wrong in the construction?
Several circles intersecting at a point. So you want something like several balloons coming together.
I could draw two red lines intersecting in the same point.
Yeah.
The original circle. So what would go wrong there?
Well, it wouldn't correspond to anything in the space I've defined, the closure of the Mn in the big torus. I mean, it might be interesting, but it would be a different subject.
The reason why it should be
well, saying that if you have a smooth surface, saying that it has a hyperbolic structure is not a very strong statement. Most surfaces have hyperbolic structures. The three-dimensional case, we got a hyperbolic structure only by cutting out some essential parts of the manifold. I wouldn't expect. Well, who knows? I don't know whether there's some substantial part of the higher things which are hyperbolic, but I don't know. I think hyperbolic manifolds are much rarer in higher dimensions, but it could happen. Yes?
If you replace R with C, is there an analogous story? Or?
Oh, yes. Much of what I said works just as well over C, but of course, there are differences. There are big differences. I mean, one big difference is that if you said when you split up a transverse intersection over the reals, there are just two ways of doing it. But over the complex numbers, if you split up a transverse intersection, there's a whole circle of ways of doing it. So it's connected, and it's a very different situation. But things like for example, the embedding of MR cross MS in MN, that goes over exactly the same way in the complex situation.
Am I correct in thinking that in the work of McDuff and Salomon, that they're thinking of these as coming up as boundary values of maps polymorphic disks, and there's some doubling where you get from the real to the complex things?
I really don't know how it comes in. As you see, the whole discussion is in an appendix, which is probably added as a sort of afterthought, but I can't answer that question.
Wondering, in terms of the North Pole projection of the plane, you could obviously try that instead of a circle. You could do it with an end sphere, couldn't you?
Yes.
What happened?
Well, Good question. I mean, let's see, you still have a, I suppose the appropriate group would be the group of conformal transformations of a sphere. And I have no idea what would happen. It's a good question. Yes?
So you called M5 the hyperbolic dodecahedron?
Yes.
If I recall correctly, there's another 3-manifold, which is also called the hyperbolic dodecahedron, taking a regular dodecahedron, like a solid one, and identifying the sides in a certain way. Is there any sort of relation between the two, or is it just a naming coincidence?
That one's actually called hyperbolic dodecahedral space. I don't think it's the same thing.
I don't know if you heard there. That's a classical construction of a hyperbolic 3-manifold, but it's called it's 3-dimensional, and it's called the hyperbolic dodecahedral space.
So part of the theory that Stashev did was that these associated Eastern have an A-infinity operatic structure.
Yes. Yes, this is...
Mimics for the MN. They also have an operatic structure.
Yes. Some of these papers make heavy use of operatic structure and MNs. That is, I just defined this one map from MR cross MS to MN, but there are many multiple maps from products of MK to MN, and they all fit together with a complicated operatic structure, which I didn't try to describe. But that plays a central role in some of these papers.
I'm sure there are many other questions that people would like to ask, but perhaps they can be asked in private. Let's thank Jack now for a beautiful talk.